Hello, I am Christian Malaga, and this short video will review the most relevant aspects of the Laplace transform. The key concept discussed is the definition of the Laplace transform and its most relevant properties. The Laplace transform is a powerful mathematical tool that allows us to turn partial differential equations into ordinary differential equations and to convert ODEs into much simpler algebraic equations. Hence, it is a very convenient method for solving the equation of motion, particularly when the forcing function is of discontinuous nature and cannot be solved easily by other means. The Laplace transform of a function f in t, which is defined for all positive values of t, is the integral from 0 to infinity of the function f in t multiplied by a kernel expressed as e elevated to minus st, where s is a complex quantity called the Laplace variable. This Laplace transform is often indicated by the script letter L or a capital letter F. The basic idea of transforming a differential equation into a polynomial equation rests upon the definition of the Laplace transform of derivatives. To this end, the Laplace transform of the first derivative of f in t is defined by this expression. By using integration by parts, this equation can be expressed as e to the minus st times f in t evaluated from infinity to 0 minus the integral in time from 0 to infinity of minus se elevated to minus st multiplied by f in t. This equation can be simplified to obtain this new expression where f parenthesis 0 is the value of the function f evaluated at time t equal to 0 and capital F parenthesis s is the Laplace transform of f. Likewise, using a similar approach, the Laplace transform of the second derivative of f of t can be simplified to obtain this expression, where f dot at 0 is the value of the first derivative of the function f evaluated at time t equal to 0. More generally, the Laplace transform of the nth derivative of f in t can be found by adding s to the n times the Laplace transform of f minus s to n minus 1 times f evaluated at t equal to 0 minus s to n minus 2 times the first derivative of the function f evaluated at time t equal to 0, and so on. This is a key feature of the Laplace transform and one that we will use in class to solve the equation of motion. Another property of the Laplace transform is related to shifting. In some cases, the function f appears together with the term e elevated to at, where a is real or complex. The Laplace transform of this product can be obtained by adding up the exponents, which results in the Laplace transform big F shifted by the amount a in the S domain. Finally, another important property of the Laplace transform is related to convolution. In cases where the function f of t is the result of the convolution of two functions, f1 of t and f2 of t, both defined for t's greater than 0, its Laplace transform can be expressed as the multiplication of capital F1 and capital F2 that are the Laplace transforms of small f1 and small f2 respectively. Like with the Fourier transform, this implies that a cumbersome operation, such as convolution in the time domain, can be more efficiently carried out in the Laplace domain where it becomes a multiplication. These properties will be of great use when solving ODEs of dynamic systems in terms of s rather than time, which makes them amenable for representation in the form of block diagrams that are easier to manipulate in many cases.